the last class, we have studied about what is the splitting field. Let us quickly revise it. So, splitting field is something in which we can split your given polynomial into linear factors, right? So the formal definition for that is, if you have some polynomial f of x having degree greater than or equal to 1, then the extension field k of f is called the splitting field of f if your polynomial that completely factors as a linear factor. So that means if you have some polynomial f of x, that polynomial is written into the product of linear factors of this form, where all these coefficients, they are coming from the upper field k. And moreover, you can write this upper field extension k as the smaller field f, where all these elements alpha 1 up to alpha n, they are adjoined to it. So, and what are these elements alpha 1 alpha 2 up to alpha n? They are the roots of the given polynomial f of x. So suppose alpha is the root of this polynomial f of x, that means x minus alpha 1 would be a factor of this. Say alpha 2 is the root of this polynomial, so x minus alpha 2 would be a factor of this one. And similarly, if alpha n is the root of this polynomial, then x minus alpha n is the factor of this particular polynomial. So you can write the complete polynomial fx as the product of these all factors. So this is the definition. So in the last class, we have also studied about the examples of this field. For example, we have this polynomial x square minus 2. So what are the roots for this polynomial? First root is square root 2, another root is minus square root 2. So its factor are, this one is x minus 2 and another, according to this root, is x plus square root 2. So both these are linear factors, and the coefficients of these factors, they are from this field q, where square root 2 has been adjoined to it, right? Because 1 obviously belongs to this field of rationals, whereas the square root 2, yes,
आपकी आवाज भी नहीं आ रही है अच्छे से, आपका सीन हो रहा है हमें.
beta, is your internet connection stable?
Yes ma'am.
Okay. So we have this example where we were seeing x square minus 2 as a polynomial whose splitting field is this field of rational numbers, where square root 2 has been adjoined to it, right? So this was the first example. The second example was, yes? So the second example here is that of complex numbers. So here we take the polynomial x square plus 1. One of its root is x is equal to iota and another root is x is equal to minus iota. So according to this root, we have this factor x minus iota, and according to this root x is equal to minus iota, we have this factor x plus iota. So we have factorized this polynomial into linear factors of this form, where the coefficients are available in this extension field c, which could be written as the real numbers, where we have adjoined the element iota to it. So this is another example. Let us see the third example. In the third example, we have this polynomial x cube minus 2. Now this polynomial, we have to show its degree is 6. So for seeing its degree, firstly we have to determine whether this is an irreducible polynomial or not. So for irreducibility, we have this Eisenstein's criteria, which says that if you find some prime number such that it divides the coefficients apart from the first coefficient, then the given polynomial is an irreducible polynomial. So here the prime number is 2, so this prime number 2 divides a naught, the constant term. It divides the first term, which is 0. It divides the second term, which is again 0, and it does not divide the third term, which is 1. A3, the coefficient of x cube, which is 1, right? And moreover 2 does not divide this a naught square, right? So all the conditions of Eisenstein's criteria is fulfilled, therefore we say this is an irreducible polynomial. And we know what would be its root. One root would be, if I substitute this is equal to 0, I have x cube is equal to 2, and I can write x is equal to 2 to the power 1 by 3. So this is one root. So now if I have one root, that means x minus 2 to the power 1 by 3 is its factor, right? So if this is one root, so that means this is one factor, so I can divide this factor, this polynomial, through this factor, and I'll obtain the quotient as this particular factor. So now we can call this polynomial as px, and we are interested to calculate its roots. So that means according to this factor we have got one extension field of this field of rational numbers. So when you adjoin this 2 to the power 1 by 3 to it, you have one extension field, and this is not the splitting field yet. Why? Because all the factors of this polynomial x cube minus 2 are not present in this particular field. So we have to find some other polynomial extension field which is present over here, in order to calculate its splitting field where all the roots of this polynomial are present. So for that, firstly we have to check what is the degree of this polynomial field over this field. So for that we check what is the degree of this field over this field. So to have the degree of this field over this field, the field of rationals, we will look for the degree of this irreducible polynomial. So its degree is 3. Therefore the degree of this polynomial field, extension field over this field of rationals, is 3. So this is one thing. Next we have this polynomial. So let us find what are the roots of this polynomial. Now it is not so easy to find the roots of this polynomial, so we assume that alpha is one root, alpha bar is another root. So if alpha is root, alpha bar is another root, so I can adjoin this element alpha to this field, the lower field, so that the new field now has all the elements 2 to the power 1 by 3, alpha, and alpha bar as well, right? So that means we found a field where all the roots of this polynomial x cube minus 2 are present. So that means we can say this is the corresponding splitting field. So we found the splitting field for this polynomial, and what would be the degree of this field over the given field of rationals? That would be equivalent to the degree of this field over this field multiplied by the degree of this field over this field. Its degree we have found to be 3. What would be the degree of this polynomial? From moving from here to here, we have just adjoined an element alpha to it. So whatever is the minimal polynomial whose root is alpha, that would be our irreducible polynomial. So this is the polynomial that we are talking about. Its degree is 2. That means the degree of this field over this field is 2. So we have its degree as 2. So the degree of this extension field, this field over this field, that would be equivalent to the multiplication of these two. So 2 multiplied by 3, so that is 6. And what are the basis elements? We know here only this element has been adjoined, so basis elements are 1. Say this is u is equal to 2 to the power 1 by 3. So 1 u raised to power 1, u raised to power 2, and that's it, right? Because here the polynomial has degree 3, so we'll go up to degree 2. So we have 1 2 to the power 1 by 3 and 2 to the power 2 by 3. And then for alpha we have, on moving from here to here, only this element has been adjoined, and the basis elements are 1 and alpha. Why up to alpha power 1 we have gone? It's because the degree for this alpha, the degree of the polynomial alpha having its root as alpha was 2. So we went up to the power 2 minus 1, that is 1. So this is the basis for this field, this is the basis for this field. So the basis for this upper field q to the power 1 by 3 comma alpha, that is the linear combination of all these 5 elements. So you have 1 into 1, 1 into 2 to the power 1 by 3, 1 into 2 to the power 2 by 3, then alpha into 1, alpha into 2 to the power 1 by 3, and alpha into 2 to the power 2 by 3. So that is it, right? So this is the definition for splitting field.